Alright, so we're going to finish up chapter 22 today and talk about reactions that can be used in conjunction with EAS reactions. And so we've learned several electrophilic aromatic substitution reactions throughout this chapter, and we'll look at them some more in the next chapter, but for now we're going to talk about reactions that we can use after an EAS reaction. So the first thing we're going to look at is the synthesis of benzoic acid. And so before I talk about the new reaction that we're about to learn, let's think about how we would synthesize benzoic acid using what we know. So benzoic acid looks like this, where we have a benzene ring directly connected to a carboxylic acid. So if we were to go through this with the reactions that we know, we see that we have CO2 here. And so we can make this carbon electrophilic, and we can make a Grignard out of our aromatic ring. So we just learned, if we start with benzene, we just learned that we can brominate benzene using Br2. Remember, Br2 by itself doesn't work, so we have to use a Lewis acid. So we can either use iron tribromide or aluminum tribromide. Either one would work in this case. I'll just use iron, and this puts a bromine on our ring. And so we get to a compound like this. Now we could do a variety of different things with this bromine. We could do cross-coupling. We could turn it into a Grignard, which is what we're going to do to synthesize benzoic acid. So now we get our Grignard reagent, and now we just need to add this CO2 molecule here. So we would use CO2 in our first step. That would serve as our electrophile, so our Grignard would come in and attack. We move the electrons out onto one of the oxygens, and then we need a step 2 to protonate it. And this would get us to our benzoic acid. So now let's talk about a new reaction of how we would synthesize this. Alright, so let's talk about a new reaction to make benzoic acid. And that's going to be using KMNO4 and potassium hydroxide. We've talked about this reaction before where we oxidize alcohols to carboxylic acids. And we said this wasn't a very good oxidant because it can oxidize a variety of different functional groups, which is true. It does provide us one way to oxidize the benzylic carbon to a carboxylic acid, and so we need at least one hydrogen on this benzylic position or for it to be part of a pi bond. And so the outcome of this, when we use KMNO4, KOH, followed by an acid workup step, is benzoic acid. And so like I just said, you need at least one benzylic hydrogen or for it to be part of a pi bond. So even if we have something like this, so even if we have something like this, where our benzylic carbon is part of a pi bond, it's part of two pi bonds in fact, in this molecule, we still get oxidation to the benzoic acid. Alright, so the only way that we would not have this reaction occur is if we had no benzylic hydrogens and our carbon is not part of a pi bond. And so that would be something that would look like something that looks like this. So we have a tert-butyl group. We see our benzylic carbon here is not part of a pi bond, and it has no hydrogens on it. So if we tried to take this and do this oxidation reaction, we would get no reaction. But in pretty much every other case, it will oxidize the benzylic carbon to the carboxylic acid. It'll even do it if we have a long alkyl chain. So if instead we don't use this molecule, we use a molecule like this, we see that our benzylic carbon has 2 hydrogens, so it has at least 1. And we treat it with potassium permanganate, potassium hydroxide, followed by an acid workup. We're going to get benzoic acid. Alright, and we're not going to run through the mechanism for this. It's thought that it's a radical process, and we'll talk more about radical reactions in chapter 25. Alright, the next reaction we're going to talk about is reducing nitrobenzenes to aromatic amines, and aromatic amines are called anilines. So we learned how to do the nitration of benzene earlier in the chapter, so we could do the nitration followed by a reduction to get to the NH2 or the amine, which we call an aniline. There's 2 different reactions we can use to do this, and so the first one is using hydrogenation. So H2 with palladium on carbon, and this reduces this to the aniline. And so now we have our amine. Remember, these are the same conditions that reduce alkynes to alkanes and alkenes to alkanes. And so you would not want to use this reaction if we had some type of alkene in the other part of our molecule. Remember, benzene rings don't act like alkenes, and so this is not going to hydrogenate it. But if we had some other alkene in our molecule, say we had something like this, we would not want to use these conditions because it would give us the alkane from the alkene. So the second way we can reduce our compound, I'm going to take away this part of the benzene ring here. Alright, the second way we can reduce it is to use HCl and iron, followed by sodium hydroxide. Alright, so first step, HCl and iron, followed by a second step with sodium hydroxide. Why is the second step important? It's because when we're in strongly acidic conditions like HCl, our amine can be protonated. So after step 1, we're going to actually have NH3 plus on here, and then when we throw in the sodium hydroxide, we get to our neutral NH2 amine. So again, this proceeds through a radical process, so we'll talk more about it in chapter 25. Alright, let's take a look at an example here. So let's say we want to synthesize this molecule using benzene as our only source of aromatic carbons, and otherwise we can use whatever other starting materials we want. So that means that we've got to start with benzene here and make this carbon-carbon bond somehow. We've got to start with benzene here and make that carbon-nitrogen bond somehow. And then we've got to make this nitrogen-carbon bond here as well. So I think those are our 3 retrosynthetic disconnections, and so we'll work through one at a time. We know that we can acylate nitrogens using acid chloride, so I think this is probably the best thing to, or the best place to start. So we'll do this retrosynthetic disconnection first. And so we can get back to these 2 molecules here. And we know that if we use pyridine as a base, then our nitrogen can attack this. We'll kick those electrons up, kick the electrons down, kick out the chlorine, and make it into this amide here. So now we need to think about how we're going to start with benzene here and start with benzene here. We just talked about how to make aromatic amines, where the nitrogen is directly bound to the benzene ring. And so maybe that's how we want to make this bond here. So then we need to think about how we're going to make this bond between this nitrogen and this carbon. There's a couple different ways we could approach this. One of those ways would be we could do a reductive amination with our molecule, and so that would mean that we need a aldehyde on this part of the benzene ring. Alright, so now in the forward sense, I could take my nitrogen and my aldehyde, that would make an imine, and we can reduce imines with sodium borohydride to get to our amine. So these two molecules can get us to there. We still need to work backwards to benzene, and so we know how to get to both of these molecules shown here. For this, we just talked about it. We can reduce nitro compounds to the corresponding amine, and we learned how to do nitration earlier in the chapter. And so we can get all the way back to our benzene molecule. We can nitrate it, reduce it to the amine, and that gets us to here. Now how do we make this aldehyde? So we just learned how to oxidize the benzylic position, and so we could think backwards. But remember, the oxidation we just talked about gets us to the carboxylic acid. Do we know how to go from carboxylic acids to aldehydes? We learned that earlier in the semester, where we convert the carboxylic acid to the acid chloride, and then acid chlorides can be reduced with LTBE to get to the aldehyde. So we want to take the acid chloride, treat it with LTBE, which is going to get us reduction to the aldehyde here. Where does the acid chloride come from? It would have to come from the benzoic acid. And then how do we make this? We have to have at least one benzylic carbon on our molecule. And so, let's see here. I'm going to come back down here. And we would need to have a molecule like this, where we have at least one benzylic carbon on it. We could treat this with KMNO4, and that would get us to here. We learned how to do this earlier in the chapter. We could do a Friedel-Crafts alkylation of benzene itself. And so now we've gotten back to benzene here, and then in the forward sense, we can work our way all the way back to this molecule. All right, let's talk about another reaction we can do subsequently after an EAS reaction. So we're going to talk about benzene diazonium salts. And so we take aromatic amines, which we just talked about how to make this from something like benzene. We then treat this with sodium nitrite, NaNO2, and HBr. And it gives us our benzene diazonium salt. And so this nitrogen has 4 bonds to it, so it has a plus charge on it. I'm not going to run through the mechanism for this. It's quite long, and I'm not going to hold you responsible for it either. All we need to know is N2, nitrogen here, is an excellent leaving group, and so we're able to do a variety of different reactions with this molecule. And so I'm going to erase this reaction. Well, I'll just keep it up here. We're going to take this molecule and look at the different reactions it can do. Alright, so all of these reactions, so if you use a benzene diazonium salt, and any of the following reactions I'm about to draw up, we call this the Sandmeyer reaction. And so the Sandmeyer reaction converts diazonium salts into a variety of different other things. So we can treat it with copper chloride. And copper chloride takes the benzene diazonium salt to the aromatic chlorine. We already know how to do chlorination directly from benzene, so this isn't the best way to do it. We could just use Cl2 and iron trichloride instead. But we can do this reaction with benzene diazonium salts. We can use copper bromide. And that does the same thing as copper chloride, except it puts the bromine on there to give us the aryl bromide. Again, this isn't the best way. We can do this with Br2 and iron tribromide, but we can do this conversion. Some of the next reactions I'm going to talk about are useful because we don't know any other way to make these kinds of compounds. So we can put a nitrile group on there. We can use copper cyanide, and that puts the nitrile group on there. So we don't know any other way to put a nitrile group on a benzene ring, so this is the best way to do that. We can use Ki. So potassium iodide, and this puts the iodine on there. We have not looked at putting iodides on there. The halogenation we learned earlier in the chapter is best done for chlorines and bromines. So if you want to put iodide on there, this might be your best way to go about it. We can put fluorines on the molecule. And so we can use HBF4 and some heat. This puts one of these fluorines onto our molecule. So I think this is one of the first times we've seen how to add a fluorine to a carbon to make a fluorine-carbon bond. So this is a particularly useful reaction, and it's the only way we know how to put fluorines on the benzene ring. We can convert it to a hydroxide group. Like this with the OH, and that takes H2O. Copper oxide, so H2O, CuO2, copper oxide, and CuNO3, so copper nitrite, and this converts us to our phenol. Lastly, we can just take this whole group off and put a hydrogen on there. So if we use strong acid, like phosphoric acid, H3PO4, we just get a hydrogen on there. And so we can go from our aniline molecule to this diazonium salt, and then go all the way back to the benzene ring using these reactions. And so these are all of the types of Sandmeyer reactions, and some of them are useful to put things on the benzene ring, like the nitrile, for example, because we don't know any other way to do that. All right, let's take a look at one last example here. So these aren't going to involve Sandmeyer reactions, but it will involve some reactions we learned in this chapter, as well as other reactions we've learned earlier in the semester. So this is similar to types of exam questions you've seen before, where you got to tell me what A, B, and C are. And so let's go through this. We see we have a benzene ring, we have this acid chloride, and we have aluminum trichloride. We recognize that these are the conditions for a Friedel-Crafts acylation, and so we're going to make a carbon-carbon bond from our benzene ring to this carbonyl. So A is going to end up looking like this. So this is going to be our methyl ketone here. Then we're going to take this and treat it with excess Cl2 and sodium hydroxide, followed by H3O+. So what the heck is going on here? There we go. Camera was kind of blurry. So what the heck is going on here? We have sodium hydroxide and Cl2. We know Cl2 is an electrophile, so we need some type of nucleophile. This is neutral right now, so it's not very nucleophilic. Then we have sodium hydroxide, which can act as a base if possible. So sodium hydroxide is capable of deprotonating this alpha carbon, and so once we deprotonate it, that gives us our nucleophile, and that attacks our Cl2. Once we put one chlorine on there, remember that these protons become even more acidic, so we end up putting 3 chlorines on there, like that. And then this becomes a good leaving group, and so our hydroxide is able to attack here. We kick up, kick down, and kick out our carbon with 3 chlorines on it. So this is the haloform reaction, and we end up converting methyl ketones to carboxylic acids. So this is our product after reaction 1. For B, it's going to be a carboxylic acid. And then we've also seen that we can convert carboxylic acids to acid chlorides, and we typically use SOCl2 to get that done. And so our final compound here would be this acid chloride. Now we know that we could go even farther with acid chlorides. We can reduce them to aldehydes, and we can add in nucleophiles. For this particular example, this is our answers.